Well, I think we're good at this point. So without further ado, I'd like to introduce Rose Jansen, who's with the Academy of Science, St. Louis. She does so much to put these wonderful programs on, and we're so delighted to have our relationship with the Academy for these programs. Thank you.
So good evening. We're glad you were all able to make it here tonight, and there really truly are some seats over here. There are a couple on the very end of the aisle here, and there are 6 or 7 seats down here that are easily accessible, so please come on down. We're very pleased to bring you science seminars in partnership with the St. Louis Zoo, and as Louise said, my name is Rose Jansen. I'm with the Academy of Science St. Louis. And for those of you who are not familiar with the Academy, I'm going to take just a moment to tell you a little bit about who we are. We're an independent science organization. We're supported entirely through community contributions. We've been connecting science in the community for a very long time, since 1856. And it's our long-standing mission to advance the understanding of science and inspire the next generation of scientists and science advocates. And we do that through a very broad range of free and low-cost public science programming, programs for teens, adults, families, middle school students, and educators that include citizen science, inquiry-based learning opportunities, collaborative seminar series, and trips and tours. They all highlight science at venues throughout the metropolitan region, and you can find more information on the Academy and our community-wide events, public talks, and programs by visiting our website at academyofsciencestl.org. You may also visit us on Facebook or Twitter, or pick up some of our literature that is outside the auditorium on your way out this evening. If you're interested in helping to support the Academy's many science opportunities for students and adults throughout the metro region, there is some membership information also at the table just outside the auditorium. And if you'd like to receive e-notification of upcoming Academy public lectures and events, there are some e-news sign-up sheets that will make their way around the audience. If you're a student and you need to verify attendance, we will have cards that you can pick up from us tonight, also at the Academy table outside the auditorium and following the Q&A. I do want to mention some upcoming events you might have an interest in attending, and in particular, you might want to mark on your calendars the next in our science talks here at the zoo. On Wednesday evening, December 4, from 7:30 to 9 p.m., here in the Living World Auditorium, 2012 Academy Outstanding St. Louis Scientist Innovation Award recipient and Assistant Professor of Pediatrics and Molecular Biology talks about, at Washington University here in St. Louis, talks about fighting malaria in the 21st century, the current challenges in the control of malaria worldwide, and the exciting promise of studies to develop new vaccines and treatments. And then on Wednesday evening, March 5, also from 7:30 to 9 p.m. here in the Living World, Academy trustee and Sun Edison chief scientist, Dr. Graham Fisher, talks about semiconductors in from sand to silicon. And on Wednesday evening, April 2, one of the world's foremost Alzheimer's disease researchers and 2013 Academy Outstanding St. Louis Scientist Peter H. Raven Lifetime Achievement Award recipient, Dr. John Morris, will be here in the Living World to talk about advances in Alzheimer's disease research. And then very quickly, I'm going to mention a couple events on biodiversity that are up and coming that you might have an interest in attending. We invite you to join us on Thursday, November 14, from 4:30 to 7 at the Missouri Botanical Garden Monsanto Center for Wild Ideas Worth Sharing. It's an inaugural speaker series event that kicks off the Biodiverse City Project's public seminar series launched to encourage and promote networking, learning, and envisioning a more biodiverse St. Louis region. Registration is required and seating is limited. There are some flyers outside the auditorium with information on the program, or you may log on to our website both for more information and to register. And then lastly, on Tuesday, November 19, also here at the St. Louis Zoo from 5:30 to 9 p.m., you don't want to miss the 2013 Whitney and Anna Harris Conservation Forum with a panel of speakers on energy production and biodiversity. This event is free to attend, but again, you do need to register, and you can find more registration information and information on the event itself on our website at academyofsciencestl.org. We have many, many, many science opportunities, talks, and tours on our website, or again, listed on the flyers and Academy literature that's available for you to take with you before you leave tonight. So with all that said, I'm going to introduce tonight's speaker, Dr. Joseph Lykken. Dr. Lykken earned his BA in physics from the University of Minnesota and his Ph.D. in physics from the Massachusetts Institute of Technology. He is currently a senior scientist with the Fermi National Accelerator Laboratory in Batavia, Illinois, and his research interest includes supersymmetry, dark matter, Higgs physics, extra dimensions, and string theory. And rather than read to you a litany of Joe's accomplishments, selected and invited keynote talks, briefings, lectures, professional publications, and noteworthy accomplishments, and they are many, I thought I'd share with you the following. Joseph's 9th grade science teacher told his parents that he taught Joe everything he could and that they should seek more advanced opportunities. Joe had a paper route at that time, and as luck would have it, the Star Tribune offered its carriers a Saturday meeting with representatives of 2 Eastern boarding schools that were seeking to broaden the socioeconomic range of their student bodies. The school that appealed most to Joe was Phillips Exeter Academy in New Hampshire, and Exeter was happy to accept him. At Exeter, he got a C+ in nuclear physics and was almost kicked out for an egregious violation of the fire code. Joe is now a theoretical physicist at the Fermi National Accelerator Laboratory. And so the message is believe in yourself, never give up in your pursuit of science. Dr. Lykken is here with us tonight to talk about the Higgs Boson and the fate of the universe. On behalf of the Academy of Science St. Louis and the St. Louis Zoo, won't you please join me in welcoming Dr. Lykken.
Should work. All right. Well, thank you very much for inviting me. Thanks to the Academy and to the Zoo for hosting this. It's a pleasure to be here. This is my first time at the St. Louis Zoo. My older son and his girlfriend, who have been to the zoo many times, tell me it's one of the best zoos in the country, one of the best zoos they've ever been to, so I'm going to have to come back in the daytime to see what it looks like. Although I have to say, even though I've never been here before, I feel strangely at home here. It's almost as if I feel I belong here. I don't quite know why that is, but it seems like a wonderful zoo. So here's a little outline of my talk. I'm going to talk a little bit about the Higgs boson. Can you see the pointer when I do the pointer? Kind of. 4th of July fireworks, that's because it was discovered on July 4th or the discovery announcement was on July 4th of last year. So I'll talk a little bit about the Higgs boson discovery, what went into that. And then the second half of the talk is sort of the what now. So you discovered this particle that you've been looking for 20, 30 years, 40 years in the case of Mr. Higgs. What now? What does it mean? Where do we think it's going to take us in science? And I'm going to talk about 2 things. One is the possible connection between the Higgs boson and the ultimate fate of the universe, which is something we won't be around to see, but it's certainly of academic interest. And the other is possible connection between the Higgs boson and the mysterious dark matter that holds our universe together. So let's start with the fireworks. That's an artist's rendering of the fireworks of making Higgs bosons. My entire story tonight takes place in this galaxy, which is the Milky Way galaxy. It's actually in this solar system. In fact, we can be even more specific. It's on this planet. And most of it will be on this continent, which is called Europe. And there's a country here called Switzerland. And if you zoom in on it, there's a nice lake here called Lake Geneva. There's a small city called Geneva, which has been there for a very long time. The Rhone River comes out of the lake here and goes into the Rhone Valley, and they have wine and stuff down here. So it's a very nice area. You might not connect Switzerland with the idea of science, but in fact, it is one of the most important science center, certainly for physics, in the world today. The Europeans have made a huge investment there in science, and it's not in these boats, it's not in these buildings here where they have a lot of private banks. This is downtown Geneva. It has something called a public transportation system that's probably not familiar to you. They have Alps. They also have something called a national healthcare system in Switzerland. But this is what's relevant to my story is the CERN laboratory, which is one of the largest scientific laboratories in the world and also one of the most international science laboratories in the world. It's a European laboratory. It's paid for by a consortium of European nations, but also has major collaborations, as you'll see, from the United States, Japan, and other countries. Now, again, as I said, Switzerland you might not associate with science, but there is an interesting science connection to Switzerland, and it goes back not so much to Geneva, but to this town which is almost identical to Geneva, which is Zurich, which is a little ways away. In fact, you can get from one to another on something called a high-speed train, which is another concept you're not familiar with. But Zurich also has a lake, and it has old buildings, and in particular, it has the Café Odeon, which still exists. It's been there for at least 100 years, more than 100 years. It's a beautiful place to go, especially on a cold, rainy day, to get out of the cold and have a coffee or a more harder drink. And if you had been to this cafe, not now, but in 1905, you might have noticed both of these people sitting there, probably not together, although I don't know. The details have been lost to history, but we know that, in fact, they both were patrons of the same cafe at more or less the same time. And they were also more or less doing the same thing in that cafe. They were plotting revolutions. Mr. Trotsky plotted a revolution which he then carried out some years later in association with some other people. And Mr. Einstein carried out another revolution also in association with some other people of a very different type. And I leave it to you to figure out which of these revolutions had a more lasting effect. I think I know which one had a more positive effect. But that's not really the subject of my talk, but I wanted to remind you that the reason this gentleman was in Switzerland was that the only job he could get at that time was in the Swiss Patent Office, partly because his genius had not been realized, and partly because of anti-Semitism, which kept him from getting a job in Germany until sometime later. So that's a proud history of Swiss science, and while we're on the subject of Einstein, I also wanted to mention this quote because it gets to the question you always get when I give a basic science lecture like this is, okay, what is the Higgs boson good for? How do you make money off of Higgs bosons or make weapons out of Higgs bosons? And you don't do any of those things. It costs money. You don't make money. But it has to, I think this is a great description of why we do this kind of stuff. I cannot be in awe when I contemplate the mysteries of eternity, of life, of the marvelous structure of reality. And it's enough if one tries merely to comprehend a little of this mystery every day. And I really like this phrase, the marvelous structure of reality. That's what we're doing in this basic particle physics and cosmology that I'm talking about. We're trying to understand the marvelous structure of reality that's out there and how it's put together, what it means, and not necessarily to make money off of it. So let's go back to Geneva, Switzerland. If I zoom in a little more, this is a little bit outside of Geneva, the town. In the countryside, these are farms and vineyards. And if you were able to dig down here, you would find that there's a particle accelerator called the Large Hadron Collider. This is a ring. It's about 100 meters underground. It's 27 kilometers around. There's, inside of this, as you'll see, there's magnets and high voltage equipment that are designed to accelerate particles to very nearly the speed of light. And then they're made to smash together at certain places around this ring. And at the places where they smash together, we have particle detectors, which have names like CMS, which I'll talk about, Atlas, another one, Alice, and LHCb. And so basically the idea here is to have particles going very, very high energies, almost the speed of light, smashing into each other, and then these detectors are figuring out what happens in these very high energy collisions. So here's an actual aerial view. Here, again, you see the ring which somebody has drawn in because you don't actually see a white line there, but it shows you where it is. This also gives you an idea of the scale. This, again, is Lake Geneva. This is the Geneva airport. So I like this picture because when you see that somebody actually bothered to build something that's bigger than an airport in order to do science, that is a major commitment. This is, again, as I said, this was mostly done by the governments of Europe, but we can be proud in the United States. In the United States, we have spent more than $1 billion of your money to build this thing that's bigger than an airport, and is designed only to do basic science. It's not designed to make any money or have any military applications or anything like that. It's designed to figure out the marvelous structure of reality. Now, it turns out this is not the first large thing built on this site. When they were building the above-ground parts of the CMS detector, where the control room and other things are, they actually discovered the ruins of a Roman farm that was 2,000 years old. And that's because the Romans were the first people to civilize this particular area outside of Geneva. And the ruins of the farm are interesting in many ways. They found some old coins. What's especially interesting is that the way the Romans had laid out this farm, the way the straight lines, you can kind of see it here, are exactly the same way that the farms now are laid out. So the Romans laid it out 2,000 years ago, and that's exactly the way everything is now. They did it correctly the first time, and that's the way all the farms are still laid out. The other thing this reminds you of is that this area was first visited by the Romans when Julius Caesar came here in 58 BC. And the reason he came here was because at that time, the people living in the Rhone Valley, which was a more or less civilized area, were being threatened by the Swiss who had come in from the east. And the Swiss at that time were a warlike people, a fearsome warlike tribe of people. And so Caesar came there to defend the civilized people of the Rhone Valley from these terrible warlike Swiss. But he didn't actually have, as usual, he didn't have enough soldiers with him to actually do the job. So instead, he had his soldiers build a wall that went basically from the lake here over to the foothills of the Jura Mountains as a temporary expedient to keep the warlike Swiss out until he could get reinforcements. So it basically went across this site here. He didn't have to worry about getting government grants and environmental impact statements or any of that. So he built the wall in about 3 months. Whereas this that we're now going to talk about took 15 years. But it's not the first large thing on this site. So if you go down inside the tunnel, you see this. There's the actual beam, what we call the beam pipe, where the very high energy protons go, is quite a small pipe. It's sort of this big around. But it's surrounded by these big blue magnets. And the purpose of the big blue magnets is to bend the beam, because once you have charged particles going almost the speed of light, they want to go in the straight line. They don't want to go in a curved line. But the reason we want to make them go in a curve is because every once in a while, at several places around the ring, we give them a kick. So they go around and around and around and around this circle many, many, many times, each time getting another kick until they get up to the energies that we're looking for. This is the world's narrowest fire truck, which can actually drive around on the ring. We don't have to use it too often, although I will remind you of an incident that happened that was related to that. This is my contribution to the LHC Accelerator. This is also a very powerful magnet. It was built at Fermi Lab. It's red because it's a different kind of magnet. It's built to actually focus these beams before we bring them into collision. I didn't build the magnet. I didn't design the magnet. I didn't move the magnet and install it here. The thing that I did was I put this sticker, the American flag sticker on. That was my contribution. That was the only time I was allowed to touch the LHC Accelerator. But still, it was very interesting to see the whole thing. This is another view which is relevant to what I'm going to talk about. These magnets here, these are superconducting magnets. In order to not use all the power in the world, they're made superconducting because they have huge amounts of electricity running through them. That makes them much more efficient and powerful. But in order to be superconducting, they have to be cooled to 2 degrees above absolute zero. Well, there's about 1,200 of these magnets. They each weigh about 15 tons. So that's about 20,000 tons of stuff that in order to make it work, you have to keep it at 2 degrees above absolute zero all the time. So how do you do that? Well, the way you do that is you have this big pipe here, this white pipe. This pipe is full of liquid helium that circulates around the 27-kilometer ring. The liquid helium is as cold as you can possibly want, but it's a lot of liquid helium. There's 20 tons of liquid helium here in order to keep these magnets superconducting. And that, again, will also play a role in our story. So this is, in addition to being the world's largest particle accelerator, it's the world's biggest refrigerator by far. So how does it all work? Well, I'm a particle theorist, so this is the best I can do. Scientists make sure on-off button is switched to on. That's actually the most important thing. Parts of machine begin to move, at first slowly, then rapidly. A lot of science, this part I know is true. A lot of science. Sounds of, this is not supposed to happen, the sounds of thunder. Also, this is also not supposed to happen, science ends. But let's do a little more, let's zoom in a little more on our movie. So if you go down to one of these underground caverns where you have the detector, so the detector is not the accelerator. I have the accelerator, I have these particles smashing, but now I need to know what happened. And for that I need a detector, which is a whole separate thing. And for that we have big collaborations of scientists that build these detectors. They have big pieces. This is where the beam goes. So the beam is just a little pipe in the middle here. And then there's about $1 billion worth of electronics and other specialized devices that surround the beam, and they're supposed to detect all the high energy particles that are coming out of this thing. So the CMS detector is about $1 billion worth of fancy electronics and magnets and all kinds of things that are designed to capture all of the high energy particles that are coming out of these collisions. So now if I'm a proton, I speed up to the speed of light. I go inside this detector. I find another proton going the other way. Boom. And lots of other things come out. And then your job as a physicist is you don't sit down underground there. You sit up in the control room, and you see these computer reconstructions of what happens. And these are actual events, and as you can imagine, they look like a big mess. Furthermore, only 1 in 10 billion times do you produce something like a Higgs boson that you're really interested in. So most of the time, this is nothing, and this is the needle in the haystack problem. So you want to sift through these. In the end, it's trillions of events like this, each of which is a big mess. And 1 in 10 billion times, find the one that might have a Higgs boson in it. And that's your job as a physicist, is to do that sorting out from all these trillions and trillions of collisions. So this is not, sometimes you think of experiments as, okay, I set up the experiment and then it's ready, and then I do the experiment and the next day I'm done. It's not like that at all. These are experiments that take years and years of time. The first beam for the LHC was in August of 2008, so that's almost, well, it's more than 5 years ago now. This is actually the first, this is the beam monitor. This is what we call the beam spot. This was the first time we actually saw beam in this thing. This is Lynn Evans, who actually designed and led the team that built the accelerator. So you can see they were all happy on that day. A couple of weeks later, they were not so happy. CERN likes to call this the incident. It was actually by far the biggest catastrophic accident ever having to do with high energy physics. What happened was these superconducting magnets are joined together. They're actually joined together by soldered connections, but they're supposed to be really good soldered connections. And most of them are really good, but one of them was not. And it had 8,700 amps of current flowing through it when it failed. And the superconducting magnets became non-superconducting magnets. They then dumped all their stored magnetic energy as heat immediately. This sent a pressure wave, basically an explosion in both directions on the tunnel, because that was the line of least resistance. About a ton of that liquid helium that I showed you in that pipe became gaseous helium in a few seconds. And so all of the oxygen for a large part of the whole underground complex was displaced by helium. Fortunately, there was nobody there at the time. There had been people there about half an hour before. If there had been people there, they would have died from helium, death by helium, because they would not have been able to breathe. And about 53 of those magnets, which remember they weigh about 15 tons each, they were thrown around like child's toys by this explosion, and 53 of them were destroyed. And the explosion went about 4 kilometers, 2 kilometers in each direction along the beam pipe. So that was bad. It gives you an idea of the kind of power that is involved in this machine, and also what a non-trivial, what sort of a daring idea this is to try and make a machine like this and to get it to work for years at a time when it has that kind of power going through it. Now, actually, in the experiments, we were kind of happy. Well, we weren't happy, but we were a little relieved that we had an extra year, as it turned out, to get the experiments ready. Because, as I said, this is another $1 billion worth of electronics that you have to get working. These pictures always have a person in them, so you can see how big these things are. So there's a person looking down. This is the Atlas detector. The Atlas detector weighs about the same as the Eiffel Tower. It's much more complicated than the Eiffel Tower. It's very hard to get these things up and running. Same thing with the CMS experiment. The CMS experiment, this thing is actually covering another magnet, a superconducting magnet. This is by far the world's most energetic magnet. It has 2.7 gigajoules of energy when it's powered up. You got to be really careful when you turn on a magnet like that, because things move when you turn it. This has enough stored energy to stop an aircraft carrier. So the first time they turned that on, they thought they had figured out how everything was going to move, and they were almost right. But there was some scary moments. So it takes a lot of people to do this, as you might imagine. So just the CMS experiment, so that's the people that run that one detector, the CMS detector. That was, at the peak, it was about 4,000 people. It's on average, it's something like 3,000. It's scientists, it's engineers, it's computer people, and it's almost 1,000 students. A lot of students involved in this. 40 different countries, including the US, 193 different scientific institutes. It's so many people that you can never put them in one place. So this is just a small fraction of this scientific collaboration. Completely global, international collaboration. So as I said, about a year went by before the machine was turned on again. This time it worked, so that was good. And finally, on November of 2009, they reached the highest energy collisions that anyone had ever reached before. The previous record was held by Fermilab, my laboratory, which used to have the world's highest energy collider, but no longer does. It's also not a coincidence that the people that were running the experiment when they first got their collisions were Americans. And the reason for that was because we had the experience. We had at Fermilab, the world's highest energy collider, also other accelerators in the US. So we had the people that knew how to turn these machines on, these detectors on, and make them work. So in fact, not only were the US people involved in this experiment, we were involved in running things right from day one because we know how these things actually operate. This is what we call the spokesperson. When you have 3,000 scientists, somebody has to be there to make them behave. That's the spokesperson. This is our former spokesperson, Jim Verdi, and it's also his job to get the champagne when something good happens and hand it out. So as I said, it takes years to sift through all these events. So you've got everything working, and now you've got your computers that are analyzing all your data. The data rate coming out of the LHC experiments was about a petabyte a second. It shut down now for some improvements, but while it was running for more than 2 years, there was about a petabyte a second coming out. That's comparable to the total anything of anything in computing. In fact, it's too many computers. It's too much data for any one site of computers to analyze. There's a lot of computers at CERN. There's a lot of computers at Fermilab. We're one of the primary data analysis sites, but it's still not enough. So one of the things that made the LHC possible, made it possible to discover the Higgs boson, is that there's something called the worldwide grid. It's a way of doing distributed computing where you can have data coming out from CERN. It immediately goes all over the world to a bunch of other computing sites, and all the analysis is done distributed all around the world. So it's not just the World Wide Web that was invented at CERN. The LHC was one of the pushing the technology of this worldwide grid of distributed computing because we had to. That's the only way you could analyze this much data. Okay, so that was hard, and I'll give you some more ideas a little later on about how hard all this was. But after about 2 years and a few trillion collisions, both Atlas and CMS announced at the same time a discovery. And this was, as I said, on July 4 of last year. This is the Director General looking awestruck. This was a packed room at CERN in their largest auditorium. People had camped out the night before in order to get a seat. We had a live feed at Fermilab where unfortunately it was 2 o'clock in the morning because it's 7 hours earlier, but still people were pretty enthusiastic. Peter Higgs was here at CERN in the auditorium. He was sitting slightly to the right here. He was crying, as you might imagine, because as he said, I never expected this to happen in my lifetime. These were the 2 spokespeople at the time of the discovery. This is Fabiola Giannotti, who's a CERN physicist from Italy, and this is Joan Candela, who's from UC Santa Barbara, who is American, who was the head of the CMS experiment at the time. It got a lot of press coverage. Fabiola got on Time Magazine's cover as one of the people of the year, so that's pretty cool. This was the first time the entire New York Times science section was devoted to one subject, so that's pretty cool. And I think in general, the world understood that this was not just something that happens every day. This was the world's largest scientific project to date. And the fact that it was successful and successful really in a relatively short time was pretty amazing. And as I said, I like to toot the horn of the United States because you paid for it, you might as well be happy about it. We are about 1/3 of the CMS collaboration. We're the largest contingent. So even though this is a European laboratory, we're doing this all the time because we are the largest contingent in CMS. We're one of the largest contingents in the Atlas experiment. As you saw, we had a spokesperson. We have all kinds of people all the way down the line doing all the important jobs. It's a total from the US of 1,700 scientists, students, engineers, technicians from all around the country, including the national labs and universities. So you should be proud. This is an American achievement. It's not just a European achievement. It's a global achievement of science that had a lot of US leadership. The other thing I wanted to point out is that the old people, which I define as people of my age, were not the ones that were analyzing the data and making the discovery. The old people's job was to do management, to be spokespeople, and to be involved in sort of the science politics that keeps the collaboration of 3,000 people together. And the people that actually analyzed the data and made the discovery were people that I would define as young people. They look like this. And furthermore, from all over the world. So these are just people that I actually worked with for, on LHC data for both for Higgs and supersymmetry. So this is Tiago is from Brazil, Ilaria is from Italy, Piotr is from Poland, Sezin is from Turkey, Chris is from Caltech. And so it's really, I think, inspiring to see both the fact that these discoveries are being made by young people and sort of a group of young people pulled from the best and the brightest all around the world. So you don't have to be 50 years old or 80 years old like Mr. Higgs in order to be part of a big discovery. There are people 25 years old who are sitting in the room. In fact, Emmanuel DeMarco, who's right here, he was the guy sitting in the room with 3 other people when they actually looked at the first data display that showed they had the Higgs discovery. And then the next day they went to the old senior guys and said, hey, we have the Higgs discovery, you want to see? But he was the one that was in the room when they did it. In fact, some students from the US actually won prizes for contributions to things like hardware. HCal is a piece of the detector. Trigger is the way that you figure out which events you want to keep. And they actually made contributions that were considered so essential to the Higgs discovery that they were given prizes by the collaboration. This also, I like this picture because it shows you how things operate. So here's the senior person who sort of stands over in the corner. And then here's all the young guys, and what they were doing, this is a test stand where there are cosmic rays coming in, and they were trying to figure out how to get their Mac laptop to talk to some old oscilloscope display that they had in the Caltech lab that they had never seen before, but in 5 minutes they had figured out how to make the Mac talk to it, and this is why you have to have young people. So I'm going to talk a little later about Higgs bosons and Higgs fields and this famous Mexican hat potential, which you may or may not have seen. This is the ubiquitous photo. But I don't want to get into the details of that quite yet. But I do want to tell you a little bit of the history of the Higgs boson and why we thought it was interesting. And this really has to do with the relation between basic science and symmetries. You can very famously write our standard model of particle physics, which as far as we know describes all fundamental phenomena of nature everywhere in the universe. You can write it on a napkin if you have a sufficiently large napkin. And what this is telling you is that it's not just a list of particles. It's how those particles are put together and how they interact, and the forces of nature are very, very, very strongly restricted by certain principles. And those principles we call symmetry principles that say you can do it this way, but you can't do it that way. And it's a very tight set of rules having to do with symmetries, which make it possible to understand all of this complicated world at the subatomic level in terms of symmetry. But as Phil Anderson, who is a Nobel Prize-winning condensed matter physicist, pointed out in a very seminal article in 1972, more is different. So subatomic physics has all this symmetry. Why is the world around us so complex? And of course, we know the answer. The answer is that the world around us is made of big things. We're big here. I mean, on this scale, a glucose molecule is a big thing compared to a proton. Once you start putting things together, they become many-body systems. They become macroscopic systems eventually. They have emergent phenomena that you can't predict from the underlying theory. So I've got a standard model of particle physics that describes how protons and electrons act. But it doesn't tell me how high-temperature superconductors work. In order to do that, you have to actually look at the phenomena of how the atoms are put together in much more complicated macroscopic systems. So this is understood. Condensed matter physicists understand that the way you get complexity is by having things which are big. And because they're big, they have complicated features. And one of those features is that you break symmetries. So this has been known for a long time. But way back in 1960, Yoichiro Nambu, who was a Japanese-born but spent most of his career at the University of Chicago, he was very interested in all this condensed matter stuff and all the symmetry breaking that you have in condensed matter physics. And it occurred to him that you could start to apply some of these ideas to particle physics, and in particular to properties of the vacuum. Now, this is one of the craziest and thus also most inspired ideas, I think, of modern physics, because you think of the vacuum as being empty, right? The vacuum is where you have nothing. And so what's the relation between having nothing and complicated systems like magnets and crystals? But as he understood, the vacuum isn't really nothing because it's a quantum vacuum. In quantum mechanics, the vacuum isn't really empty. It has all kinds of funny quantum vibrations happening in it all the time, and there's not really any such thing as an empty vacuum. So the vacuum has properties, and furthermore, it's big. It's the whole, most of the universe is the vacuum. And so it is like a crystal. It's a big thing, and it has funny, complicated properties. And now you have to figure out what those funny, complicated properties are. And as Nambu realized, one of the properties the vacuum could have is the vacuum could break fundamental symmetries of physics, just as crystals and ferromagnets and more familiar systems break symmetries, just by the properties of the vacuum. This was a Nobel Prize-winning idea, and in fact, he describes this very well in his Nobel lecture. But it's really an amazing idea that what we ought to do in particle physics is study properties of nothing, of the vacuum. So just a few years later, by 1964, a whole bunch of people have jumped on this idea, and Peter Higgs and several other physicists realized that, in fact, the vacuum could have very, very, very interesting properties. In particular, there's a particular kind of force field or energy field that has to do with particles called bosons that could actually exist in the vacuum and could give the vacuum interesting properties, and those properties could do things like give other particles mass. This is what we call the Higgs mechanism, the fact that a particular kind of energy field can give mass to other kinds of particles. The Bose in boson, I'm going to say boson a million times in this talk, this is actually named after another physicist, an Indian physicist named Bose, who was a contemporary of Einstein, more or less. He worked for a railroad company. He was not a tenured professor anyplace, but he understood that there's two kinds of particles in nature. One we now call fermions, after Enrico Fermi, also Fermi lab named after him. And the other kind are called bosons. And the bosons have special properties, and one of their special properties is that they can make energy fields that are just spread out through space. And that's the idea that Higgs had in order to explain how other particles get mass. So we make this discovery of the Higgs boson last year. I helped organize a couple of meetings after the discovery, the title of the meetings was Higgs Quo Vadis, Higgs, where are you going? Because we were trying to understand, well, we had this discovery, now what? Where are we going now? In the case of Mr. Higgs, we know where he's going. He's going to Stockholm, and he will be there on December 12th of this year because he's getting one of these things from the King of Sweden, as is Francois Englert, who also wrote one of the 1964 papers. Sadly, Robert Brout, pictured here, who was an American, and wrote the key paper with Englert, didn't live long enough to win the Nobel Prize because it is one of the non-negotiable rules of the Nobel Committee is you have to be alive to win the prize. So everyone, of course, in the particle physics community, including the people that discovered the Higgs boson, were incredibly excited by this Nobel Prize and very happy for both Higgs and Englert. They certainly deserved this recognition for something they did a long time ago that finally has been verified. But now I want to get a little bit back more to the experiment and how we know anything about the Higgs boson or what it has to do with anything else. I told you that it's important that it has to do with giving mass to other particles, but how do we know any of that stuff? How do what do you see in your detector that you say, oh, that's a Higgs boson? Well, one of the things you have to worry about is how do you make a Higgs boson in the first place? We think we understand that. We think that there's stuff inside the proton called quarks and gluons. So this gray ball is supposed to be a proton. It has other stuff inside of it. Protons are not elementary particles. They have other things inside of them. Quarks and gluons, and those quarks and gluons, when we smash together two protons, can occasionally, through some funny quantum processes, they can produce a Higgs boson. That's what this H0 is supposed to be here. So we had some idea how often that would happen, but it was discouraging because it was only about 1 in 10 billion of these collisions at the energy that they were running. And so that told us this was going to be very hard. Once you make a Higgs boson, it's an unstable particle. That's why they're not sitting around in this room. The reason you have to make them by high energy collisions is because they're very unstable. Once you make them, they only live for about 100 yoctoseconds before they decay into other particles. Does everybody know what a yoctosecond is? Raise your hand if you don't know what a yoctosecond is a trillionth of a second. It's the shortest period of time for which there's a name. So they decay into other lighter particles. And they do that because they can, because they talk to all the lighter particles, because they're giving them mass, and so they decay into them. So then you have to figure out, well, what are all the things you can actually look for that could have come from the Higgs boson? It could have come from, for example, this will be one of the things we use for discovery. If you see 4 electrons, E here is for electron. If you see 4 electrons and you put them together in a certain way, those things could have come from the decay of a single Higgs boson. They actually do it in 2 steps. The Higgs decays into 2 other unstable particles called Z bosons, and each of those can decay into a pair of electrons. The Higgs boson can also decay into 2 photons. This was another method we used for the discovery. And then there's lots of other ways it can decay, but it was these ones that we actually used for the initial discovery. So what do you actually see in the detector? Here's a Higgs boson candidate. I say candidate because you never know if one particular collision like this was a Higgs boson. You can say there's a good probability it was a Higgs boson, but you never really know for sure. But it looks like a Higgs boson. Here's again, you have the beam is going this way. You have the collision in the middle. You get a bunch of junk that goes forward and a bunch of junk that goes backward. But then there's 2 very high energy photons that could have come from the decay of an unstable Higgs boson. So this is an actual event that probably is the Higgs boson. Not so easy to reconstruct those things. Those photons are detected in something called the electromagnetic calorimeter. The electromagnetic calorimeter is made out of 80,000 of these crystals. These crystals are transparent, but they're made out of metal. They're made out of a combination of lead and tungsten. So that's already a tricky thing right there, transparent metal. They're transparent so that the light can get through them, but they're made out of metal because it's a high energy photon and you want to stop it, so you want something heavy. And then you have to make this device work with the 80,000 crystals, and that means you have to have a laser running through it using the laser light to calibrate this thing. This is something that was built in the US and is operated as the experiment runs. And just making that laser work is already a major scientific project to keep those 80,000 crystals running. This is the other Higgs decay channel they talked about that we use for discovery. So that's the Higgs boson going to 2 of these other particles that we already knew about called Z bosons, and then each of those going to, here L stands for either an electron or a muon, which is a heavier version of an electron. So you can have 4 electrons or 4 muons or 2 electrons or 2 muons. And this is what those look like. Again, it's a pretty dramatic event. There's some junk that goes forwards and backwards, but then there's very high energy particles that we can identify. But even this is not so easy. This is what we call the golden channel because it's relatively clean compared to other messy things. But if you actually zoom in and look at those collisions, you notice that what actually happened here, so this is the direction of the beams, it's this direction. You actually notice that there wasn't just one collision when you produce this Higgs boson. In this particular case, there were 50 collisions that happened at the same time. That's because we're trying to make as many collisions as we can, so we have a bunch of protons, another bunch of protons that go through each other, and most of the time you don't just get one collision, you get a bunch of collisions. So you had 50 collisions, they all made a bunch of stuff, and only one of these is the one with the Higgs boson, and so you have to understand all of this at the level where you can say, oh yeah, those 4 particles that I said come from the Higgs boson, they came from interaction number 7 here, not the other 49 next to it. So that's not so easy either. Now I'm going to condense all of that, all of the technical and time that went into this and show you the data compressed down to 12 seconds. So there's the ATLAS discovery of the Higgs boson in 2 photons, condensed down to a few seconds. And at the end of the day, what you have is a bump. So for the 2 photon case, what you have physics that isn't the Higgs boson, that has a predictable shape. In this case, you see it's just a smooth shape with some statistical fluctuations. You can't get away from that. This is quantum mechanics. It's got statistical fluctuations. And then there's a bump. And so when you stand up and say, I discovered the Higgs boson, what you really mean is, I discovered this bump, and I have a good story for why that bump is a Higgs boson and not something else. And it better be a very good story. Here's the same thing for that golden mode that involves electrons and muons. This, I think, is actually more convincing, although there's other things you have to talk about here because there's more than one bump. So here again, I'm showing you the real data from CMS. All these black dots are the real data. And then the blue stuff here is our prediction for some bumps that we thought should be there anyway. This bump, which is actually the biggest one, comes from Z bosons. Remember I talked about Z bosons as something the Higgs can decay into. Z bosons we already knew that existed. We know what their mass is. It's about 90 in these units. And so we expected a bump there. We got a bump there. You can also produce at these energies 2 Z bosons. If you do that, you get another bump that's at sort of twice the mass of 1 Z boson. So that's this other bump here. And then there's not supposed to be any more bumps. But there is. So Here, you don't have to be a rocket scientist to realize that there's something you didn't expect here. This is the Higgs boson. Now, you might also notice there's another bump there, and we're still looking at that one. We don't have a statistical statement that's very convincing for that one. But it brings up an interesting question, which is, are there any more Higgs bosons? And this is one of the most important questions that we're looking at now when we turn this machine back on and run it for another 15 years, is you found one Higgs boson. We had never seen anything like a Higgs boson before. Now we've seen them. How many kinds are there? And we think there might be many kinds. We have theoretical ideas that I like, but who knows if they're right, like supersymmetry, that say there have to be at least 5 different kinds of Higgs bosons, and we've only found the first one. So there's good reasons to look for these things. They're different. They have different mass. They have different properties. This is supposed to be Higgs with different mass and different properties. And so you don't exactly know what you're looking for, but you kind of know what you're looking for because they should be similar to the Higgs boson that we found. So that's one of the big things that we want to do in the future. But now for the rest of the talk, I want to concentrate on Higgs connections to other kinds of questions. In particular, I'm only going to have time for the first two, which is, does the Higgs destabilize the vacuum and destroy the universe? And then, is there some connection, some what we call portal, between the Higgs and dark matter? There's other interesting questions that I can't talk about. The Higgs has some connection to neutrinos that we'd like to understand. It may actually have been possible for the creation of all the matter in the universe, so that's kind of important. And then there's other mysteries of cosmology that have to do with cosmic inflation and dark energy that seem like they should be related to the Higgs, but we're too stupid to understand the connection so far. And this is probably for the next, 20, 30, 50 years, these questions are going to consume a large fraction of the physicists in the world trying to understand this kind of science. So let me first talk about the question of vacuum stability. So I want to start by talking about force fields. So I said there's a Higgs boson, that's a particle. And then I said there's a Higgs field, this boson field, which is an energy field. So we're kind of used to the idea of force fields, but I want to remind you that when Michael Faraday, who was the first person to suggest that there really are invisible force fields in the world, his colleagues thought he was nuts. And you can kind of see why, because it doesn't sound like physics to say that there's invisible force fields that are sort of everywhere. What does that mean? But we've gotten used to that. We've gotten used to it, for example, in the case of magnetic fields. The Earth produces a magnetic field. And you can understand that, and one of the reasons we believe it is because for example, has a direction. So if I have a compass, the compass points in the direction of the magnetic field. So it's an energy field that has a direction, so you can see that it's there, and then you can see how the direction changes. And the other thing is that it has a source. So the magnetic field is there because the Earth is there. The Earth is a big ball of metal and stuff. So there's a reason why the force field is there. It's there because there's something that acts as a source. So here's the Higgs field. This is what we now believe we have proven to be the case. The Higgs field is also an invisible force field, but it doesn't have a source. It's its own source. It turns itself on. It doesn't require the Earth or anything else. It permeates the entire universe. It doesn't have a direction, so there's no compass. You just have to believe it. So this is why we spend a lot of money finding the Higgs boson, because you're never going to believe this unless you have some very closely related prediction that you can go out and test. But now we believe it, and in particular, this gets us finally to the Mexican hat. This has to do, so this is just a mathematical representation of when you have force fields, you can ask how much energy does it cost to turn this field on by a certain amount? And what you would normally expect is that the thing that costs you the least energy is to have the field turned off. I have electrical fields in my phone, for example, and if I turn the phone off, then the fields go off because that's the lowest energy state for them to be in. But that doesn't have to be the case for these boson fields. Because they have self-interactions with themselves, they can get into a situation like this, where having the field turned off, which is being in the middle here, can actually cost you more energy than turning the field on by a certain amount. Now, if you turn the field on even more, that's going up the brim of the hat here, it again starts to cost you energy. So there's some sweet spot, which is around here, where the energetics of the way this field interacts with itself tells you that it wants to turn itself on by a certain amount. And this is what we think is happening with the Higgs field. We think it's turned on, it turns itself on everywhere in the universe by a certain fixed amount. That amount has been fixed since the early days of our universe. And that is responsible then for giving fixed masses to all the other particles, almost all the other particles. So that's what the Mexican hat is supposed to represent. So in that sort of picture, now I'm going to show you a little cartoon. You're living happily here at the bottom of this energy well, this Mexican hat. This represents what we thought is the lowest energy state for the vacuum, so this is where the vacuum should be. It is indeed where it is now. We have verified by experiment. And so that's the end of the story, right? Well, you can ask the question, well, what happens if I turn the field on more and more and more and more, and I go out this direction? Does anything interesting ever happen? And that's a calculation you can do. We have a quantum physics theory now. It's a theory that's very precise. You can do very precise calculations, and you can answer a question like, what happens if I keep turning on the Higgs field? Does anything interesting happen with the Mexican hat? And this is the answer. The answer is it does this. So this is where we are now. So that's good. But if you eventually turn the field on enough, you get over the hump here, and you get to a spot where it's energetically favorable to be here rather than here. So by turning on the Higgs field even more, you can get to a more favored universe, a universe that's energetically favorable compared to the one we're in. The reason we're not there, presumably, is because of this bump here. You have to get over the hump, if you like, in order to get into the preferred state of the universe. So that's bad news, because in quantum mechanics, anything that can happen will eventually happen, and that's not good, because that means we're living in what's called a false vacuum. There's a true vacuum, or maybe some kind of runaway situation, and eventually there's some little quantum fluctuation that's going to happen somewhere that's going to get us into the true vacuum, and that fluctuation it'll be energetically favorable for it to expand as a fireball that will consume everything. And this idea has been known since 1979 that this might be the case for the Higgs boson, but it wasn't known until last year what the numbers were, and it was only last year that we were able to put in the numbers and see that indeed this seems to be the case. The press went crazy with this. Fox News, Higgs boson may spell doom for universe. So you can imagine that. Now the good news is that this probably won't happen for 10 to the 100 years, which is a long time. In yoctoseconds, it's really a long time. On the other hand, if you're super unlucky, it might have happened already, and you won't know because this is expanding at the speed of light, but you don't have any warning that it's going to happen. But you might as well not even worry about it. I would advise you to keep paying your taxes because the chance you'll get out of them is small. But what's really interesting to us as physicists is that this calculation that I talked about, it depends on the mass of the Higgs boson, which is the thing we've just measured. It also depends on the mass of the top quark, because that has to do with the quantum mechanics that goes into this. And it turns out that this answer is very sensitive to those values. And in fact, we're right on the edge between living in a stable universe and an unstable universe. You change this by a few percent, and you go from an unstable universe, the one we're living in, metastable, because it lives a long time, to a stable universe. So why is that? Well, the answer is nobody has any clue why that is. And this is one of the big questions now that we're grappling with. It shows you how you can make a discovery. You know, the Higgs boson was expected. We expected to find the Higgs boson. And in fact, the only thing we've measured with precision about it so far is its mass, because all the other things are harder to measure, and it's going to take years to measure them. So we only measured one number about it, and that number turns out to be incredibly interesting because it tells us we're right on the edge between a stable universe and an unstable universe. And nobody knows why. So one of the things that I've been working on, and many people have been working on the past year, is to try and come up with alternative explanations for what's going on here. In particular, an obvious question has to be that we have to ask ourselves is, well, wait a minute, to do this calculation involves all of particle physics. But there's a part of particle physics that we know we don't understand, and we're not putting it into the calculation, and that's the dark matter. Most of the matter in the universe is not the particles of particle physics. It's mostly dark matter, which is made out of we don't know what. And so before you can make a statement like this, you have to understand what's the effect of dark matter, if any, on the Higgs boson, or the Higgs boson on the dark matter. So this is the intersection between physics and astronomy, and this is something you find more and more in particle physics these days. This is actually, at CERN, they named the streets this way, so on the lab site. So this is an actual intersection at CERN. Dark matter, of course, has a long history, and I could give you a whole lecture about dark matter, which I will not do. It goes back to the 1930s with this charming gentleman, Fritz Zwicky, the first to suggest that most of the universe is made out of dark matter. This was proven astronomically by Vera Rubin much later in the 1970s by observations of galaxy rotation curves. And nowadays we have tons and tons and tons of data that show us that, in fact, most of the universe is made out of dark matter, not out of ordinary matter. And this is done indirectly through the gravitational effects of dark matter. The fact that dark matter exists is known only through its gravitational effects. It does things, for example, like what we call gravitational lensing. It bends the light coming from distant galaxies. So that's a gravitational effect caused by very, very large amounts of dark matter. But we know there's dark matter. There's lots of it. It's most of the universe. It's complicated. But what is it? So every little kid knows there's dark matter. So in particular, one of the big questions is, how does dark matter interact with ordinary matter? We know it interacts gravitationally, because that's how we know there is dark matter. Does it interact any other way? Well, if it interacts any other way, it must interact very weakly, because otherwise we would have seen it already in laboratory experiments, or even from astronomical observations. So what's a way to interact with matter that's very weak? Well, in the standard model, we have something called weak interactions that involve this Z boson that I talked about before. These weak interactions have been known for a long time. They are responsible for the first step of fusion in the sun. They actually determine how long the sun lives. So they're very important. They're very weak. And that's one of the obvious candidates for how dark matter would talk to ordinary matter. But now that we know there's a Higgs boson, the Higgs boson has a force associated with it. So maybe it's the Higgs boson that talks to the dark matter. And maybe that's the thing we should be trying to understand with dark matter. Well, this turns out, again, to be a very interesting story. You have to put in a little bit more theory, because you need to have some idea what is, when you say dark matter, what do you mean? And we think that dark matter is particles. We think they might be heavy particles. We don't know this for sure. They might be light particles instead. If they're heavy particles, as I said, they should be interacting very weakly with ordinary matter, probably interacting very weakly with themselves as well. And this particular kind of hypothesis for dark matter is what Michael Turner, famous cosmologist, calls WIMPs. And so when I talk about dark matter, from now on, I'll be talking about WIMP dark matter. This is a hypothesis that could be wrong, but we think it's the leading idea for dark matter. And in fact, we have lots of experiments now that are sitting down in mines. This is a mine in Minnesota called the Sudan mine, where we have super sensitive detectors sitting down at the bottom of these mines that are looking for very, very weak signals of dark matter coming in from outer space. Since there's lots of dark matter, there's lots of dark matter coming in from space. And by having very sensitive detectors that are shielded from everything else, the hope is you can actually do what we call direct detection of dark matter particles coming in from space. And this is CDMS, this is a Fermilab-led experiment, is one of the experiments trying to do this right now. So these direct detection experiments so far have not seen any signals of dark matter that we can confirm, at least. There's some hints, but nothing you can really confirm. And that allows you to make a plot like this that says, well, if the dark matter interacted too much with ordinary matter, then I'm up on the high part of this plot, and that's already ruled out by the fact we haven't seen anything. If it interacts very weakly with ordinary matter, then I'm in the low part of this plot, and I'm still okay because you wouldn't have expected to see anything. So with the Z boson, which is the ordinary weak interactions, you're already doomed. They're not weak enough. The ordinary weak interactions are not weak enough to explain why we haven't seen dark matter in these experiments like CDMS that I showed you there. On the other hand, if the Higgs boson had turned out to be 500 GeV, that's about 3.5 times heavier than it actually is, then you would be depressed, because in that case you would expect that these experiments are many orders of magnitude, this is a logarithmic scale, many orders of magnitude away from being able to detect dark matter through the exchange of Higgs bosons, through the Higgs force. But that's not what we have. What we actually have is a Higgs boson who's in GeV units is 125, and that puts you here on this plot. So in fact, if dark matter interacts weakly through ordinary matter through the Higgs boson, the one that we found, then you would expect these experiments to find direct signals of dark matter in these underground mines in the next 5 years. So this is one of these great coincidences of technology and science, that we might be right on the verge of finding a signal which will turn out to be the Higgs boson talking to the dark sector and the dark matter, which I think is incredibly exciting, and that's why I'm working on these kinds of ideas. So that's good. So let me kind of summarize now, what is the LHC telling us? It's telling us, be careful with your solder joints. when we turn the machine back on, we're going to almost twice the energy. So when they crank up the current beyond what they ever had it before, everybody's going to be holding their breath. So, but they say it's going to be okay. What's the true meaning of this Higgs discovery? Well, I don't know. I hope I've convinced you that we don't know. I think it's the beginning of something. It's a story that I think bridges all the frontiers of particle physics and cosmology. It seems to, as you might expect, the Higgs connects to everything, and it connects to everything in ways that we don't understand. So that's great, and it's a story that has to do not just with particle physics, but also with cosmology. I told you something that might have to do with the end of the universe. I didn't have time to tell you about something that's a connection between the Higgs and the birth of the universe, but the Higgs may be responsible for the creation of matter in the first place. And there's many surprises. I showed you some surprises that we've already had, and I think there'll be many more surprises. But what's especially encouraging to me is that we've already seen that in addition to surprises, we're able to actually get at this stuff with experiments that are within our reach. So having made the investment that we have in this kind of basic science, we have the technology, we have the people, we have the international collaborations, we have a way to put all this together and actually get at this science, and it's going to be in our lifetimes that these big things are going to be figured out. We're going to figure out what the Higgs boson really means. We're going to understand what dark matter is really made out of. We're going to understand big questions that have been around for a long time, and our generation is going to be the ones that figure it out. So it's not the end. Thank you very much. It's the end of my talk, though. I would be happy to answer questions. Yes? Yeah, so this is an interesting question. So we run the collisions 250 million times per second. And what limits how, we could actually have the collisions more often than that. But the problem you have is that these things collide and stuff comes out. The stuff that's coming out is going very, very fast, and we're trying to catch all of it in these big detectors. So you're limited here by the speed of light. If I have a detector that's 50 meters across, which is what we're talking about for the Atlas detector, at the speed of light, it's simply not possible to read out the information from the events in less than a certain amount of time. And so it's actually the speed of light that sets the rate at which we can do the collisions. It's not the computing power, because once we get these guys out of the detector, we can put them in a kind of a pipeline where they kind of wait a while until the computer has time to go look at them. So we can build a delay into that. But the thing we can't build a delay into is when is the next collision coming? And that's what limits the rate. Yes?
So you have the 27-kilometer circular track, and then you have the places where you detect the collisions. And I heard you say, I think, early on that you planned it so that that's where the collisions happen.
Yes.
If they're moving that fast, how do you know or predict that that's right where
Yes.
the collisions are going to happen? How do you know that'll happen in somewhere else too, and that's the only place you're going to be?
So that's a very good question. So first thing is, when I say it's 27 kilometers, it's actually 27.2257235. We actually know that distance better than we know any distance in science, any large distance in science, because you're exactly right. If we didn't, we'd be in big trouble. The other thing is we have what are called beam monitors. So we don't just turn it on and hope for the best. We have beam monitors that tell us as you're turning it on and as you're ramping up the energy, where is the beam and what is it doing, and where are the beams coming together. And sometimes, indeed, you find that they're coming together in the wrong place, and then you have to, this is why the accelerator guys get paid the big bucks, because they know which knob to turn to make it move to the right place, which is a real art. There's also a fail-safe mechanism that's designed, if something really bad is happening and it looks like your beam is just going to go in completely the wrong place, we have a way of aborting the whole beam and sending it off basically into the ground, because it's better to have it go off into the ground than to have it go into some uncontrolled place. They have done tests of what happens if you send the beam into some place that it's not supposed to go, and I've heard the tape recording of it. It makes a really loud noise. It's not a good thing to have it go to the wrong place. Yes?
From the almost nothing that I know about the Standard Model, doesn't seem nearly as pretty as, say, Maxwell's equations.
Yes.
Am I wrong?
You are absolutely right. So even though I claim that the Standard Model is ruled by powerful symmetries, they seem more complicated than they ought to be. And we think that's because the Standard Model is itself subject to some kinds of symmetry breakings that we haven't gotten a handle on yet. So it's already too complicated. And the real theory, the one we're trying to get our hands on, is presumably simpler than that and explains why the Standard Model has seemingly arbitrary junk built into it. But that's one of the big things we're trying to figure out. Yeah, in the back there.
In the 80s, during the surge basically of the institution created almost accidentally something that we all kind of are used to now, the World Wide Web.
Yes.
Now with this round of technology that's happening over this current decade and probably the next decade, do you feel like there's some other interesting stuff that's going on there where some experiments are happening that might have interesting incidental impact on them?
Yeah, I can give you a couple of examples of that. So as I said, we're not doing this for the technology, but when you get when you get 3,000 scientists together and engineers and technicians, and you say, do something that's impossible, in the course of doing something that's impossible, they tend to push the limits of technology because otherwise you can't do the impossible thing. So it's not the way you should do all of your R&D, but it is a good way of making things happen. So right now, there's a couple things. One of them has to do with this data analysis. The data analysis we're doing involves incredibly large data sets, and where we're looking for incredibly subtle, complicated things. So this is big data. Big data now has become a big thing for lots of people, and people do make money off of trying to understand how you go into huge data sets and find real subtle correlations and connections of things. So that's something we're ahead of the world on, and we think we have things to teach people about that might be worth money. Another thing has to do with these incredibly short timescales I was talking about, the octoseconds and all of that. That requires us to do things incredibly fast, and it requires us to have electronics and devices that respond much quicker on much shorter timescales that have been necessary for other kinds of applications. So we're pushing the frontiers of doing things fast electronically. That turns out to have, if you can do it, to have lots of practical applications that have to do with medical imaging and stuff. So the people that are physicists that are working on this already get phone calls from GE and IBM and companies saying, hey, we can build a better PET scanner with this. Tell us how to do it. So there is synergy happening there. At national labs like Fermi Lab, we give all this stuff away for free. I mean, we're a national lab. Our job is to make knowledge like that and then give it away, and companies can use it and go do something with it. Yes? Yes, so you might have noticed that the CMS and Atlas detectors do not look alike, and that was intentional because, first of all, they cost $1 billion each, so why do you have two in the first place? And the reason is because by having two, you can have them optimized in different ways so that one is good at one thing and the other is better at another thing. In particular, CMS had that big superconducting magnet I talked about that can stop an aircraft carrier. That's good in some ways because having the big magnet allows you to analyze charged particles like those electrons that were coming out. But it's bad in the sense that you can only make the magnet so big, so you can only fit so much junk inside of it. In Atlas, they don't have the big magnet like that. And so they have certain parts of the detector that work much better than CMS. And so the combination of the two, you sort of make sure that you can do everything well, you just can't do it all well in the same detector. Yes?
You had mentioned string theory earlier. What's the relationship between string theory, Higgs boson, and dark matter?
That's a very good question. So string theory was invented as a way of getting past these properties of the Standard Model where it looks complicated and arbitrary. Because in string theory, there's a single idea that says all these particles of particle physics, they all come from one thing. There's a string, a microscopic string, and it wiggles in 50 different ways, and the 50 different ways are the 50 different elementary particles. So that's a much more elegant, beautiful idea than making lists of particles with properties. And so we thought in the 1980s when I started working on string theory, all the smart people said, okay, now we've got the right theory, this is obviously right, and now we're going to predict the mass of the electron and all the properties of particle physics from string theory, and it's going to be great. turns out that string theory, although it's incredibly elegant, it also doesn't seem to prefer any particular universe over any other particular universe. So you can describe a universe like ours with string theory, but you can make the strings wiggle in another way and make the universe that looks very different from ours. So for example, if you say, what's dark matter in string theory? Well, I don't know, because I can make a string theory that has this kind of dark matter and that kind of dark matter and every other kind of dark matter. So string theory, the frustrating part about it is that on one hand it's elegant and it's sort of unique in a certain sense, but on the other hand it's sort of too good. It makes as many universes as you want, and people have even speculated that maybe all those other universes are out there, and we just happen to live in the one that we live in. But you'll have to stay tuned on that one. That's over here.
The time of decay of the Higgs boson. Could you give us an idea of, maybe related to the time of the particles going around the accelerator?
Yeah, so yoctosecond is a trillionth of a second. If you want to relate that to it's a very short time compared to the particles going around the accelerator. It is the shortest time period that we're actually dealing with in other parts of science. It actually has to do with chemistry and biology and trying to watch chemical reactions happen like a movie in real time. And that involves the scale that's called the attosecond. And the attosecond, if I remember correctly, is 1 billion times longer than a yoctosecond. So the second shortest time period that anybody is doing in science is 1 billion times longer than the yoctosecond. Yes?
The supervarying current views on dark matter winds, are they anticipated to be a single type of fundamental particle or
That is a very good question, yes. So when people first started making explanations for these dark matter WIMPs, they of course made a single kind of particle. But that seems kind of stupid because we don't have a single kind of particle in ordinary matter. We have many kinds of particles. Some of them are unstable, but there's more than one kind of stable particle. So I would be extremely surprised if dark matter turns out to be one thing. I would expect it to be more or less as complicated as ordinary matter. But we don't know yet. But it's a very good question. Yes? We don't know. They're both dark. However, even that is wrong because my colleague Lisa Randall has reminded me many times. She always tells me when I'm wrong on everything. I was especially wrong in dark matter because it's not dark, it's transparent. It doesn't interact with, the light goes through it. That's the reason why we see light from distant galaxies. It goes right through the dark matter. Dark energy is kind of like the Higgs field in that it's an energy field that's everywhere in the universe. But it's not quite like the Higgs field, so there's some connection there that we don't understand. And then if you say, well, how is dark energy related to dark matter? It might have, if the Higgs has something to do with both of them, as I was suggesting, that might be the connection. But when I start doing this, that's when you know that. You have to figure that out. Somebody in the back. Yes.
Can you reflect on the reasons for and the implications of failure of the super collider being built out in the West?
Yes. So some of us are old enough to remember that we were building a super collider in Waxahachie, Texas that would have been actually 3 times more powerful than the LHC. And everything was going great. And then a couple of bad things happened. One was that Texas politics got into it. Number 2 was that they put too many potted plants in the new laboratory they were building, and somebody noticed that and said, what are these physicists spending so much money on potted plants? And the third thing, the final killer, was that the International Space Station was costing a lot of money, and this was costing a lot of money. And at some point, somebody said, well, these things both cost a lot of money. Why do we need both of them? Which one do you guys really want? And of course, the Texas politicians said, we want the space station because there was more jobs involved in that. So, this is an example of how hard it is to do big science. It's not just the US. There's a project going on called ITER, which is a controlled fusion project that's not a US project, has some US involvement, but it's mainly France and Japan. They're having the same kinds of problems. It's really hard to do a $10 billion science project because politics gets into it. It's a lot of money and it becomes a big target. So I don't think it means it was the end of US civilization that we failed to build this thing. I think the Europeans went about it in a better way, and I think they have given us a model that everybody else should copy for how you do these projects gradually, and you're very careful about the politics as you go to each step. So I think eventually we can do these kinds of projects in the U.S. I don't think, in spite of our crazy political system, I think we are capable of doing big things. But in that particular case, we failed. Yes?
How prevalent is the Higgs boson in the universe? Do we know?
So because it's unstable, all the ones that were made originally went away. And so now if you want to make them, you have to have a very high energy source. Now there are high energy sources besides the LHC. We have cosmic rays coming in from space all the time. Some of those cosmic rays have much higher energies than the protons in the LHC. So there are things out there in our galaxy that have to do with black holes and other kinds of catastrophic objects that are natural accelerators and make very high energy processes, including Higgs bosons. But there's not a lot of them, and it's very expensive to go there and look at them there. But they are out there.
There are statements that the Higgs boson or Higgs field may be responsible for the property of particles having matter. Can you make some comments about how it does that, or what the mechanism is, or is that not correct?
Yeah, so it's not actually the Higgs boson that gives things mass, but it's the Higgs field that gives things mass. Because of course, to give things mass, you must be everywhere. Because otherwise, I can't just give you mass and then let you go your merry way. Mass is a property of it being hard for things to move. And so that's something that the Higgs field, we think, is doing from the fact that it's everywhere. So if you compare that, for example, to a magnetic field has an effect on all charged particles that are moving around, and it makes them harder to move in certain ways. It makes them want to bend, for example. So it's not that different from a magnetic field, but it does require that you believe that there's an energy field everywhere. The Higgs boson comes into it because the Higgs boson, when you put the quantum mechanics in, it says that for every field there's a particle. And so if the field idea is right, and that's hard because the field's invisible, the particle has to be there. And that's the thing that we've now verified. Yes, in the back.
What are the dangers to the people that live and work above this installation?
Thank you. That's a very good question. So this accelerator is about 100 meters underground. It's put that way for two reasons. One, it's actually easier to dig a tunnel if you go when you put things on the surface, usually the surface soil is not very stable, and this thing, as you might imagine, we need it to not sink every year when the spring comes. So it's actually better to put it underground just for the point of view of stability. But there is also a radiation component. As I said, the beam, you might occasionally lose the beam. And what happens if you lose the beam? Now, fortunately, the beam is going this way, so if you lose it, it goes off in some direction, but that direction is also underground. So it's not the case that if you have a house above this thing that you have to worry that the beam is going to go straight up and get you. That's not going to happen. So in fact, the people that live there, they're very happy. It's good for the economy, and it's good for the restaurants there. So we haven't any, and they don't have lawyers in Switzerland, so nobody's sued. Yes.
You mentioned earlier that black holes are natural particle accelerators. Can you explain a little bit more how does it work that if these particle accelerators, CERN are actually making any quantum black holes?
Yeah, so there were some theoretical speculation, which I was involved in fact, so it's partly my fault, that said, we don't actually know enough about quantum gravity and the rules of gravity to know how hard it is to make a black hole. So one of the possibilities when we turned on the LHC was that we would start to actually make little black holes. And then the question is, what happens when you make little black holes? Now, Stephen Hawking will tell you that little black holes are unstable and that they decay into other kinds of particles and radiation. And so they last 100 yoctoseconds, just like the Higgs boson. And I think that idea is right. But there was the worry that maybe that was wrong, and then if you made the black hole, that it would sink to the center of the Earth because it's heavy, and then it would just sit there, and gradually it would suck up the entire Earth, and that would be the end of the world. In fact, there's a pretty famous science fiction novel that my son turned me on to, which is a really good novel. in which it's referred to several times. It's not the main subject of the book, but it's referred to several times as the big accident, which is that they did exactly that, and that 200 years from now, the Earth was destroyed by a black hole like this. So there was actually a committee at CERN that looked at this and tried to figure out whether you could do a calculation where the answer was that the LHC would destroy the Earth. And they couldn't make a calculation like that was sufficiently plausible to get worried about it. But they did actually think about it, and a serious group of people sat down and thought about it. So far, we have not seen any black holes. We're turning on at twice the energy, so maybe we just missed them last time, and we'll see them the next time. So watch out. Yes?
So if every particle has an antiparticle, what would the Higgs antiparticle imply?
Okay, very good. Yes, so every particle, we believe, has an antiparticle, except for the particles that are their own antiparticles. Now, there's a very limited number of particles that can be like that, because, for example, if I have a charge, like the electron has a charge, it can't be its own antiparticle, because its antiparticle would have to have the opposite charge. The Higgs boson, on the other hand, doesn't have any charge. It doesn't have any kind of, not even things that are analogous to charges. It's a completely neutral kind of object once you make it. So the Higgs boson is an example of something that is its own antiparticle. Photons are another example of this. There's no antiphoton, because photons, they don't have any charge. They don't carry anything like that. So there are a few particles in nature that are their own antiparticles. The Higgs boson is one. The photon is another. We're actually trying to figure out now where the neutrinos are their own antiparticles. That's one of the big things we're trying to figure out, because it's a very special property to be your own antiparticle. Yes?
How many other theoretical particles are you looking for?
Oh, yeah, thank you. So, of course, when I talk about these experiments, what are the 3,000 people doing now once the detector's working? Most of them are not looking for Higgs bosons. There's maybe 200 people that are in what we call the Higgs group that are doing the Higgs bosons. Everybody else is looking for things that we haven't found yet. So we have all these theories like supersymmetry that predict lots of particles, but just in general, you have a very high energy collisions. You can just say, well, what are all the crazy things I could think of that might come out of these collisions? And we're trying to look for as many of those as we can. So I could show you a list that had at least 50 different results for 50 different kinds of exotic particles that we've looked for, but so far we don't have any what we call clear signals for these other particles. But again, these things are very sensitive to how heavy the particles are and how they interact with ordinary stuff. So that's why we have to continue at higher energies. We have to get more data. You have to keep doing this stuff because it's very easy to just miss something. At Fermilab, we looked for the Higgs boson. We now realize, now that it's been found, that we just missed it. We were close, and we just missed it. Yes? Oh, yeah, so that's a good question. So I said, in the collisions that we're doing, only 1 in 10 billion makes the Higgs boson. So why can't I be smart and think of a way to do the collisions in such a way that I make more Higgs bosons? So if I were not colliding protons, but I were actually colliding elementary particles, remember I said protons are not elementary, they may not have other junk. Suppose I was colliding electrons, which are elementary particles. Then I could actually collide them such that the energy of the collision was exactly equal to the mass of the Higgs boson. And in that case, it's much easier to make Higgs bosons when you're producing them. It's what we call on resonance, is when you actually crank the energy to exactly their mass. The problem is when we collide protons, we can't do that because a proton is a bag of other junk and another bag of another junk, and the collisions are kind of random in that sense. But there are ways of doing that, and there are people that have talked about making Higgs factories, colliders, accelerators that are specifically designed to do what you're talking about. Okay, let's in the front here.
You had mentioned about the Higgs field, the Higgs boson particle, and if the particles are so rare, how do we know about the existence of the field? Because isn't the field usually made up of particles?
Yeah, so the field is everywhere. the particle comes with a certain mass. And that has to do with, again, with the shape of that Mexican hat that I was telling you that controls the way the energetics of this thing works. And that mass is pretty big. The Higgs boson is the second heaviest elementary particle that we know about. If it were much lighter, which it could have been, there might be Higgs bosons all over the place, just like there's electrons all over the place. The electron is a light elementary particle. They're easy to make them all the time accidentally from all kinds of processes. So the only reason why there's not Higgs bosons all over the place is because they're heavy, and then once you make them, they're unstable. But it didn't have to be that way. Yes?
We're going to have a collision of protons, and all this stuff will give off. The thing that's collecting this information has a specific surface area, right?
Yes.
How do you know that you're collecting everything that's coming off, and that the surface area is not?
Yes. This is a very important question. So one of the reasons those detectors are so expensive is to make sure that you're not missing things. So you can miss things in two ways. One is if they go very close to where the beam is going, you can miss them because the beam has to get in and out, so there's holes there. So we try to actually instrument the regions right down to where the beam is going. And then the other way you can miss them is if your detector doesn't detect them. So for example, we make neutrinos in these collisions. And once you make the neutrinos, these kinds of detectors are not good enough to find those neutrinos. So there are particles we don't see. And this leads to what we call missing energy or missing momentum events, where you see a very high energy particle going that way, and then there's nothing going that way. And that either means that conservation of momentum has broken down, and Newton has to give back all his ideas, or it means that you made something that you didn't see. And so because we know neutrinos exist, we can actually quantify this, and I can show you lots of events where we're making neutrinos that make these imbalanced things. But dark matter is something that we can't see in detectors very easily either. So one way to look for dark matter is to look for these kinds of events that have a big imbalance. But the only way that makes sense is if you understand your detector well enough and what it is you miss and what it is you don't miss. There's two here. No, you first, yes. Okay, so the first question, does it have a directionality? The answer is no, and that's one of the reasons why it's hard to see that it's there. So you can have a field that has effects without having a directionality, but it makes it more challenging. The second question, which has to do with, well, you said, the Higgs has to do with giving things mass, but we know there's all this complicated stuff involving mass and relativity, and how do you do all that in a consistent way? This was part of the big trick of the reason Higgs and those guys won the Nobel Prize, was figuring out how it's possible for the Higgs to do what it does in a way that doesn't violate all the rules that have to do with mass and energy, momentum, and how they're related. So that's a complicated story. I actually just wrote an article for Physics Today magazine about that, so it'll come out in December, and you can read that. Yes? So we know what it means to turn on an electric field or a magnetic field, right? But usually that has to do with having the source. So I have some charges, and I arrange the charges in order to produce the field. The difference here is that the Higgs interacts with itself. So it's a case where turning it on is a question of what is the higher energy state versus a low energy state. What we call the vacuum in quantum mechanics is really just the state of lowest energy. And the state of lowest energy, you would think, would have things not turned on. But that's a question that has to do with all the quantum mechanics, not just of the Higgs field, but how it interacts with all the particles that it's giving mass to. And it turns out that the energetics of that is such that it's better to have the field on rather than to have it off. Now, this may not always have been so. We think that in the early universe it was the other way around, and that the Higgs field started off, and that it actually there was a certain point when the universe cooled off that the Higgs boson field actually suddenly realized, hey, I can reduce my energy by actually turning myself on, and doing other things to other things that lower the energy. So it's a dance between different kinds of effects that have the net result of which is that it turns itself on to lower its energy. We cannot measure it directly, but we measure it by measuring the way that the Higgs boson, which is the quantum of this field, talks to all the other particles that it's doing. And that calculation I showed you that says the universe is unstable is exactly that calculation. It's a calculation of what the field does because of the fact that the Higgs is talking to all these other particles. Yes, the friend here.
So when you have the physicists going and saying, hey, I've got this idea, and I need a machine that does this, find whatever particle, what set of engineers do you go to build that machine?
Yeah, so that's a very good question. So, of course, Mr. Higgs did not have the chutzpah to go to the particle physicists and say, gee, why don't you build this $10 billion collider and then you can verify my crazy theory. These things kind of evolve over time. I mean, the way these experiments work is you have the technology to look for certain kinds of things, and so you look for them. If I want to find something new, dark matter was a good example of this. I want to go find dark matter. What's the technology to do that? Well, it didn't exist 20 years ago. So then you go to universities and you go to engineers and technicians and physicists and you say, what would it take to find a dark matter particle that comes in from space and hits a piece of material? And over the course of about 10 years, people had some ideas and prototyped them and stuck them into mines. And that process is still going on today. And this is how you push those technologies, is by asking questions like that. So I think we're about done. I'll take one more question in the front here.
Before, like a while ago, people used to think like protons, things like electrons, like the basic particles. And now there's more like...
Yes, there's another layer.
Another layer, yeah.
Yeah.
Do you think that there'd be a layer underneath the boson, like something that could make up the boson?
That is a possibility. It is something that we're checking now. So we don't actually know for sure that the Higgs boson is an elementary particle, and that's one of the things we want to check with the new data. Once you have enough examples of these particles, you can kind of bang it into other things and get an idea of whether it really is an elementary particle or whether it's made out of other stuff that you can see the other stuff. So that's part of what we're going to be doing in the next few years. All right, I think I've used up all of our time. I want to thank you very much for coming.